So in this one we have 5-53. 5-53 we have a question that says in the circuit of this figure R1 equals R2 equals 20 ohms, R3 equals 10, L equals 2.5 henries. Determine the current versus time as long as t is greater than or equal to 0, given that v of t is the step function described in there. So I'm just going to pull the book over for this one. I'm just going to look at it real fast. So this is the circuit that we look at right up here. We have this as our step function coming in. That's our b of t. So that's the two values that we have. So again, R1, R2 equals 20, and then R3 equals 10, and our L equals 2.5. So let's go through and solve this one. So for this one, we are going to have a circuit positive, negative. We have our resistor here. We have a resistor here. We have it come around here. We have this here. We have a resistor here. And then R1 and R2, it says are equal to 20. So this is 20. This is 20. R3 is 10. And this is 2.5. And then this voltage source, does it give us our voltage source? No, it just says Vs of t. Yes, Vs of t is that step function, which I'm just going to draw it over here. It's just essentially saying that this is 0, this is 12. Excuse me. At 0, there we got our step up. That's all V of t is. Vs of t, voltage source of t. All right, so now we're going to solve this at. So one, we're going to look at right before this is switched, right before this input comes in, I of 0 of minus 1 is going to equal 0 because there's nothing happening before here. If there's nothing happening and this has never been charged before, nothing is in the circuit. There's no power, there's no current stored in this inductor, so therefore, if there's nothing happening, this has to equal 0. Now, if this was already charged up, there's some current stored in this inductor, but we're not even going to get there because it's not. So that's how that first bit goes. At 2, we're going to look at our other bit. We're going to look at infinity. So when t equals infinity, we're going to get 2 different loops here. So when t equals infinity, this is just going to become a wire, essentially. And if this just becomes a wire, because remember, this is going to saturate fully up. Once this field is fully saturated with current, and all that current has been stored in that magnetic field, it's just a wire that comes through. So at t equals infinity, we're going to draw this out as a positive and negative. We got a resistor here. We got a resistor here. We've got a resistor here. And again, that inductor just becomes a wire. That's a node, that's a node. And this is 20, 20, 10. And so if we want to go around loop 1 and loop 2, what we're going to get is in loop 1 minus Vs plus R1 I1 plus R2. What is this? This is I1 minus I2. I1 minus I2, which is our first loop. We can substitute in our values for this. Again, this is 12, this is 20 I1, and then this is 20 I2, I1 minus I2, however you want to solve it. This is loop 2, and loop 2 is simple because there's only 2 resistors, and one of them is connected between the 2 and one's not. So this is going to be R2, what is this, I2, yeah, R2, well, let's just take this one, R2, I2 minus I1 plus, what is this, R3 times I2 equals 0, and then equals 0, 2. So there's 2 equations. We've got I1, I2, so 2 unknowns. We can solve that, and if we solve that, I of infinity is going to equal I2 of infinity, and it's going to equal 0.3 amps. Okay, so now if we look at this circuit again, this is just a resistor circuit, so we can solve for our equivalent. So R eq is going to equal, so we've got these two in parallel, so that's what that is. 20 times 10 divided by 20 plus 10, and that is going to be then in series with 20. And so this is going to be 20 times 10 R1, R2, where that's going to equal to 20. And so our tau equals L over R eq. So this is our time constant for a inductor resistor circuit. L over R eq is going to be 2.5 henries divided by 20. That's going to be 0.126. And that is our time constant. And so if we want to write this out in a nice equation so that we can see for t is greater than or equal to 0, we can do the current of t is going to be, again, I of infinity plus I of 0 minus I of infinity times the decaying constant of minus t over tau. What this is saying is this is our initial current. This is our ending current. This is our initial current. And again, if we didn't have a decay constant, then it would just stay the same, which means that inductor wouldn't even exist. But since we have an inductor, we have this decaying constant over here. And if we solve this out, you're going to get I of infinity, which is going to equal, well, I of 0 is going to be 0. And I of infinity equals 0.3, because we already had that up here. I of infinity is 0.3, so 0.3 minus, and then this is I of infinity again, 0.3, because this is our total, but now we need our decay constant, which is E up, and then we need our T, so this is going to be up minus 8T, and that is I of T. And we can simplify that out. I of T equals 1 equals 0.3, 1 minus E up 8T. Close brackets. Cool. And that's how we solve 5-53.